Hello, my name is Nikolay Komitov. I'm from University of Food Technology, Plovdiv, Bulgaria. I will present our paper, Real-Time Controller 3D-Printed Robotic Manipulator for Digital Engineering Training. Introduction. The rapid introduction of 3D printing technology has led to the discovery of new possibilities in the design, production, and commission of manipulators of various types. This can be an independent development or an open access model. In the first way, the designer must have the necessary knowledge of mechanical engineering, electronics, and work with the appropriate software. The second approach is limited in terms of the fact that the model is ready, but there is a possibility of modifying some details in order to implement a better design. System description, mechanical part of the manipulator. For the purpose of the experimental setup, a MK2 robot with 3 degrees of freedom was manufactured, the production files of which are freely distributed on the internet. The printing material is PLA with a thickness of 1.75 millimeters and is a good choice as it is characterized by good strength and is easy to process. The following parameters are set for printing the robot parts: base and fill, body and fill, printing speed, nozzle temperature, heated bed temperature, nozzle diameters, layer height. The printing time for all parts is between 12 to 80 hours. Once they are ready, additional processing is required to smooth the surface of the parts and their fit. The base is composed of 2 parts, a fixed lower part attached to the pedestal and a movable upper part to which the following links are connected. The movement between the 2 is transmitted by gears, and to reduce friction, a bearing is formed by 25 steel spheres. The 2 bases are connected by an M8 bolt. Hardware part. Figure 1 shows block diagram of the hardware part. It consists development board, chip kit OC32 with PIC microcontroller, motors M1, M2, M3 of type MG996R, M4 is of type SG90, infrared modules of type HW201, camera. Software part. The program is writing in multi-platform integrated development environment, and figure 2 show program flowchart. Results. To create a model of the robot when working in virtual space, it is necessary to create an assembled unit file of step type from all the component parts of the robot. For this purpose, the SolidWorks software was used, with which all details from the STL format were reformatted in the program, and from there all details were assembled in step format. Figure 3 show robot model in SolidWorks. Figure 4 show Python application for controlling and monitoring the robot. With sliders, we can drive motors from 0 to 180 grams. A load test of the robot was performed in manual mode. In order to ensure safe operation, the robot was selected to carry various objects with weights ranging from 0 to 150 grams. Table 1 shows the result of the test. Conclusion: the use of 3D printing enables a rapid and cost-effective reproduction of mechanical components. CAD-based simulation support the analysis of the manipulator's kinematics and mechanical structure prior to physical implementation. The Python application allows monitoring of the robot's workflow in manual and automatic operation modes. The developed prototype provides a hands-on learning environment closely aligned with real industrial robotic systems. Thank you for your attention.